Okay, lesson 26, triangle problems. So in this one, it's going to be very similar to the last lesson, like I was saying there. But now we're going to be just relating it to a right angle triangle, mostly, right? So, yeah, mostly right. Um, so in this first example, let's just kind of jump into it. We have a 15-meter ladder slides down the wall at a rate of 50 centimeters per second. And it's asking how fast is the bottom of the ladder moving away from the base of the wall when it's 6 meters from the wall. So we're going to have a similar type of a situation, right? Like with that 6, am I going to be able to just throw that in at the beginning?
For some reason, I think not.
And just probably by the inflection in my voice, you can tell that that probably isn't the case. Yeah. Yeah. Yeah, no, this is changing, right? I'll draw a picture so we can see what's happening here. So here's our wall. And then our ladder, right? So our ladder is like here to here, right? So what's happening here is they're saying that the ladder is falling down the wall. And then at the same time, you can picture what would happen there. The base of the ladder would be moving away from the wall, right? It'd be moving that direction. So when it says when it's 6 meters from the wall, that 6 meters is changing, right? Like that's a specific time. So that seems like one of those things like in the last lesson that we want to take the derivative first and then put the 6 in, right? Like that's what we're after here. But the idea here will be similar. So let's give these things some variables though. So up and down, let's call this y, and let's call this x. And we also know the length of the ladder, right? So we really know the hypotenuse of that right angle triangle. Okay. So now, okay. So dy, what do we know? So we know dy dt is equal to, no. You guys are falling for it again. It's falling down. Negative. It's a vector, yeah. And guys, you can do it with meters. I heard meters and I heard centimeters. It's fine. You can do whatever, right? Your answer will just be in those units, whatever you choose there, right? As long as they're all in the same units, right? That's just the main thing. So I'm going to keep it in centimeters. So it's negative 50 centimeters per second. Okay. And then we're looking for dx dt.
Would it be the same?
No, it won't be the same. No, they're actually they're different at different times because you can picture at the top, right? It's going to be going down pretty slower at the beginning, and then faster at the bottom. And this is actually the opposite. This one's going to be moving faster at the beginning, and then slower at the end. What's that?
What were you drawing during that explanation? Because I can't see any arrows.
Oh, it was up here.
Oh.
Yeah. Yeah, so that's going to be falling really quickly to begin with, and then, or sorry, it's going to be slowly to begin with, and then quicker as it goes down. And it's like the exact opposite happening with your x. So they're not the same value, no.
But if our dy over dt is constant, that means that the y is always falling down at the same rate.
No, it won't be though. It's not always. It's constant. So yeah. So here, let's actually do it. I'll show you what I mean as we get going here. So. Okay. Yeah, so we want to look at this thing now when x is equal to 6 meters. So we want to make a triangle for when it's actually at 6 meters, right? So here, let's write that down. So x is equal to 6 meters. Or 600 centimeters, let's say. Okay, so now let's say when x is equal to 6, or 600 centimeters, let's figure out the triangle at that point. So let's figure that one out. So that'd be like a little right angle triangle we can draw. So when this is 6, we know that this one here is going to be 15, right? That one's always 15. That's the length of the ladder. And then y. So you guys know how to solve that, right? So that would just be Pythagorean theorem. Y is going to be equal to the square root of 15 squared minus 6 squared. So we get y is equal to the square root of 189, which is equal to about, meters, sorry. So I'm going back and forth between meters and, yeah, let's do that in meters for a second. When x is 6 meters. I'll change it after. So then 189 meters, which would be about the same as 1,374 centimeters. Okay, so what we've done, we figured out like a little triangle at that moment in time, right? We know what those lengths are. So now what's next is we want to set up our equation for the changing of this ladder, right? So we're just going to write it out as x squared, I'll do that first. X squared plus y squared is equal to 15 squared. Just Pythagorean theorem, right? And now we're going to derive this. So let's take the derivative. So that would be 2x times dx dt plus 2y dy dt is equal to 0. Yeah, okay. Okay, so now we've taken the derivative. Can we throw our numbers in now? Yep. yeah, we can, right? Because now that we've taken the derivative, now we can like actually throw them in for when it is exactly 6 or 600 centimeters or whatever we're using there, right? So now we can throw it in. So let's throw it in as, so it's going to be 2 times 600 times dx dt, which is perfect. That's the one we're looking for, right? How fast the x is changing. Plus 2 times, and then at that moment, y was 1,374 centimeters times, what's dy dt? Yeah, negative 50.
Is it equal to 0? Because
See?
that's 15 squared derivative. Is that why?
What's that?
The derivative 15 squared
Yep.
is of 0?
Yep. Okay, and now we're just solving for dx dt, right? So we get 1,200 times dx dt is equal to that would be negative, right? That makes sense. Okay, so 137,400. Well, no, because it was this negative 50. This is really like minus this, and then when I brought it over, it's going to become positive. Yeah. So then dx dt is equal to 114.5 centimeters per second. Yeah, right there. Yes. Okay, so now next one, we have a man 2 meters tall walks away from a lamppost that is 8 meters high at a rate of 1.5 meters per second. At what rate is his shadow lengthening when he is 2 meters from the base of the lamp? Okay, so let's draw this out. All right, so we have a man that is 2 meters tall. This is not going to be the scale. And then a lamppost that's 8 meters high, right? So if you can imagine the light's coming from here, right? And it's casting a shadow, like the shadow would be this part on the man. So let's call that S from there to there for shadow. And I'm going to call the distance from here to here D. Okay, so what do we know? So we know, there's always the lock word d dt for that distance there, right? What was that? That was equal to,
1.5.
yeah, 1.5, right? That's the rate that he's moving away from the lamp, right? So d dt is equal to 1.5 meters per second. Now, it's saying at what rate is the shadow lengthening when he's 2 meters from the base of the lamp. So that's D, right? Keeping in mind, so that's 2 meters. That's changing though, right? Seems like one of those things we should put in after we take the derivative. Yeah. And we're looking for, at what rate is his shadow lengthening, right? What are we looking for? We're looking for,
DSD.
yeah, ds dt. So we need the equation for this. So looks like I've got similar triangles going on there, right? You got like a small triangle and you got a large triangle. Let's see if we can make an equation out of that. Like, why don't we say 8 over, like, so this side over the entire bottom. Okay, so I'm going to call that D plus S. What would that be equal to? That'd be the same thing as 2 over S. Just setting up that ratio, right? Now, if we just do a little cross multiplying there, like bring this S up and the other side up, we can make that 8S is equal to 2D plus 2S. We'll collect like terms, like I'll bring the 2S over, so now we have 6S is equal to 2D. And then I'll say S is equal to 1/3 D. It's a pretty simple formula. So what's the next step? Yeah, take the derivative, yeah. So we'll say, so S is ds dt is equal to 1/3, and then dd dt. We never even ended up with a distance, do we? Looks like it doesn't actually matter, or it doesn't even depend on that. Which means that that would be a constant rate at that point. I gotta think about that one above now. But anyway. So okay, so yeah, so we'll say ds dt is equal to 1/3, and then times 1.5. So ds dt is equal to 1/2 meters per second. Okay, another classic one. So at 1 p.m. a van is 140 kilometers due north of a car. The van is traveling due west at 60 kilometers an hour, and the car is heading north at 50 kilometers an hour. At what rate is the distance between them changing at 3 p.m.? Give the answer as an exact value and then round to the nearest 100. Okay, so let's figure out what's happening here. So we've got a car. So C. And then it says due north of that, we've got a van. And then the van's traveling west at 60 kilometers an hour, right? So this van is moving this way. And the car is moving, where does it say that again? Yeah, moving north, right? So the car is moving this way. So, yeah, do you guys kind of see what's happening here, right? That the distance between them is what we're after. So we're making a little right angle triangle out of this. Maybe I'll fill that in. Let's go right to here. So it's moving this way. So we want to know the rate, right? That those 2 points are getting closer to, or getting farther away or closer to each other, right? Whatever is happening there. So we're relating this point to this point, right? Everyone's good with that? The hypotenuse of that triangle? Okay. So let's fill in a little bit more. This one was moving up this way. Oop. At, and let's even write in like the quantity, or so this was 50 kilometers an hour. And it was moving this way. The van was at 100 kilometers an hour. All right, so what do we know? Well, we know dn, so I'm going to call like north n, just for the one going north, and then west.
60 kilometers an hour.
What's that?
Isn't the car going 60?
Oh,
And
Or the van is going 60.
did I have that backwards? Sorry, my 100 was wrong. 60? Yeah, okay, thanks. Yep, okay. So then we're going to have dn dt would be equal to what?
what's N?
It's going to be north, sorry. Yeah, so n's going to be my north value, so 50, yeah. So we'll say 50. dw dt, or d west dt, would be 60. Yeah. Now, I do have a little mistake here. So the 50 though, if you think about this, this one is actually like, even though like we usually call up positive and left negative, right? This one is like decreasing, right? The distance between there. It was a certain distance from here to here, and then that distance is getting smaller and smaller, right?
Because couldn't you almost think of the 140 kilometers as a negative value? As like how far away the car was?
Yeah, you could. Yeah, for sure. Yeah, you could. Yeah. Yeah. So, yeah, so we're going to call this negative 50. Yeah, because it's decreasing. And even though the 60 is going to the left, right, which is typically negative, it's increasing. It's getting farther away. So we're going to call that positive.
So it's not about direction, it's about the
Increasing or decreasing. Yeah, exactly. Yeah. Okay. So then we know the time. What would the time be? Yeah, 2 hours. And then we're after dd dt, where d would be, sorry, from here to here. The hypotenuse of our triangle there, right? At that given moment. So the same as the last one, we got to figure out, well, we got to figure out what this triangle looks like at that specific time. Okay, so let's make ourselves a little triangle to think of what's happening here. So, oh, sorry, that should have been question mark, yeah. So we can think about it this way, right? That we'd have this, you know, this would be the car now, and this would be the van now. Okay, and like better triangle than that, but you get the idea. How far, and how far can we figure out how far this actually went?
speed and find the distance.
Yeah, we know that it would happen for 2 hours, and we know it was traveling at 60 kilometers an hour. So how far would that have gone?
120.
Yeah, 120. Yeah, so we know that this is going to be 120 kilometers, right? So you might have to do that, right? Actually use like the time that went by and the speed to figure out the distance. Okay. What about the height here? What's left? If this would have been a distance of 140 to begin with, right? That's how far it was to begin with. And then this 50 kilometers an hour is like closing the gap, right? 40, right? So this is going to be 50 kilometers an hour times 2 hours, right? So that's 100. And then you have 40 meters left, right? So 140 minus that. That makes sense, everybody? All right, so that'd be 40. And then this would be my distance. Okay, so let's figure out distance. So that's just Pythagorean theorem, right? So D will be equal to the square root of 40 squared plus 120 squared. And I'm going to round this one. This is 126.5. Yeah, kilometers, yeah. All right, so I think we have the info for that snapshot in time, right? So now let's write down the equation. So it'd be, I'm going to call it n squared, like north squared, plus west squared is equal to d squared. So then we're going to want to take the derivative of this, right, to figure out that, to bring that rate part of it into it, right? So this will be 2n times dn dt plus 2w times dw dt is equal to, and this one gets really awkward, 2d dd dt. That's why we don't like using d. Okay, so then we'll plug in what we know, right? So it's going to be 2 times, and then our north there, right? That was our 40, right? That's where we're at now. So that's 40 times, and then dn dt was negative 50, and then times 2, and then our west was 120, and then dw dt was 60. And that's equal to 2 times, I called it 126 in my notes, so let's keep it with that. It was 125 point, we're on 126.5 down there, but yeah, let's do that, 126.5. dt. If I'm off by like a decimal or two, that's going to be what happened, was right there. So, okay, so just simplifying that, I think you guys would be fine with that one, right? This would be dd dt is equal to, and we get 41.27 kilometers an hour. All right, so I ended up getting a positive value out of that. What does that mean in this context?
There you go.
Yeah, they're growing, right? The distance between them is increasing over time.